All right, are we ready to go? Austin, you got the stream running? Anybody hear me?
I can hear.
Yeah, Nathan, you're loud and clear.
My fault. Am I muted? What was that noise? We are good. Okay. All right. We are good. Let's get this show on the road, shall we? All right. So today we're going to be talking about networking. AKA networking 1 TCP/IP percent speedrun attempt. That is a gamer joke. Don't worry if you don't get it. It's okay. But before we begin, just want to mention Project Demo Day. We're going to be having a Project Demo Day on November 9th in at the Computer Club meeting that day. So we're looking for people who've done projects in the past or have a project they're working on. I don't think it has to be complete. Just have it have something to show off. It's just going to be a fun little day where we go around, show off what projects we've done. We have that link right there will be a form to sign up if you want to show off your project during that meeting. So be sure to do that. I'll have a link at the end. If you miss it, I'll probably put it on the website as well. So networking. Let's get into it. So for else to the wayside, we'll probably mention them, but it's whatever. We'll just get a general overview because there is an entire class. It is called Networking 1 that is basically everything that is in this presentation and a whole lot more. So, and we're going to be talking about network infrastructure as well. So, let's begin. So the OSI model is an abstract framework for how computer networks should work, and it is a stack. If you ever taken data structures or whatever, a stack, stuff goes in the top and it comes out the top. So the application sends data all the way down to the physical, and then the physical sends data all the way up to the application at the other end. And the top is 7, the bottom is 1. It goes physical, data link, internet, transport, session, presentation, application. And this is meant to be like a general overview of all the parts that is required to make computers talk to each other. And every device implements some portion. Not every device has to worry about every layer of the OSI model, which we'll see here in a bit. And every layer is essentially independent from each other. So you can swap out layers most of the time and you can still communicate. And this is the reason why your cell phone, which is usually on Wi-Fi or cellular service, can communicate with a device like a enterprise grade server that is on Ethernet or even serial or something like that. But yeah, so here's a little bit better visualization of the OSI model, how it works. So essentially data comes down and across and then up. So imagine this is can you see my mouse? I think you can see my mouse. I'm going to assume you can see my mouse. But so data comes in the top at the application layer over on their sender. It goes all the way down to the physical, and then it goes across the physical layer, medium. Might go up and down on intermediate like routers and switches on the way, but at the end it goes all the way to the top. But the main thing I want you to take away from this slide is that these arrows. So in theory, the application on the sending side receives the same or sends out the same data that the application on the receiving side gets. That should be how the network works. Imagine if you sent stuff and it came out completely different on the other side. That wouldn't make sense. That would be kind of stupid. But yeah, and you notice every layer is like that, where the receiver should receive exactly what was sent. I guess that should be pretty obvious. But yeah, now let's go through and talk about each of these layers. So the physical layer, which is the medium on which information is transferred. So lots of examples of the physical layer. So we have twisted pair, think like Ethernet cables over here, um, fiber optic, fiber optic cables, radio waves, copper wire. Think like telegraph. You just use copper wire. It's essentially just like a physical device. Smoke signals. If you can write a second layer for smoke signals, I'll be very impressed. But you could use smoke signals where you're like 1 puff equals 1, 2 puffs equals 0. I don't know, but you can use anything as a physical layer, and it's a layer where most between devices there's the most variability. But the thing that must be common is that in order to communicate, you have to have devices in the middle that can speak two languages. So if you have a Wi-Fi device and you want to communicate with an Ethernet device, you have to have like a Wi-Fi access point, it's usually called, which takes your Wi-Fi signal and takes your data and puts it out on the Ethernet network. So here's some exclusively layer 1 devices. So the telegraph, you just sent like bits of data in Morse code. It's essentially a layer 1 device. And an Ethernet hub, if you know what a switch is, an Ethernet hub is a really dumb switch. All it does, it takes whatever is entered on whatever port and it repeats it out all the other ports. It's just a repeater with multiple ports. And your Wi-Fi radio on your phone or your laptop is also a layer 1, as well as a cellular radio or anything like that. A few concepts you need to understand with the physical layer is simplex versus duplex. So a simplex means one-way communication. This is useful if you don't need to send anything back. So like an FM radio broadcast, you're just blasting tunes onto radio waves, But then there's duplex, which is two-way communication, which is usually more useful if you want to hold a conversation or something like that. And with duplex, there is half duplex, and then there's full duplex. Half duplex means you can't transmit and receive at the same time. So think like walkie-talkies. You can't just hold down the button and just keep talking, because then no one else will be able to talk. You have to let go so everyone else can talk. Only one person can transmit at a time on a half duplex network. And this is the same for Wi-Fi. A lot of radio-based networks are half duplex. Oops. Full duplex can transmit and receive simultaneously. So Ethernet, most of the time, you can. There's two cables. There's one cable for transmit, one cable for receive. Not quite sure why there's like 8 of them in there, but that's how your Ethernet is always faster than your Wi-Fi, no matter what. Pretty much, if you have, because Ethernet you can transmit and receive at the same time. Now we move up to the data link layer, which essentially lays the groundwork for organized communication on a physical medium. So now we have a medium where two devices can talk to each other in like bits and bytes and whatever, smoke signals. How do we organize that? How do we label which device is which? How do we get data from one point to another? That's what the data link layer is for. And it brings the concept of a local area network, or a LAN, which is essentially a group of a layer 2 capable, or layer of, just network devices that are organized at the layer 2 level. So example standards of layer 2 devices, you see IEEE a lot. 802.3 is Ethernet. 802.11 is Wi-Fi. Now, don't get confused. Wi-Fi and Ethernet were kind of physical standards too, but Ethernet also has like the data, how the data is organized on the wire. That is the layer 2 part of Ethernet. Same with Wi-Fi. Wi-Fi has like BSSID, SSID. That's the layer 2 part. As well as Bluetooth. Bluetooth is also a layer 2 standard, which uses radio waves as its layer 1. So yeah, and it and everything at the data link layer. So you'll see me refer to like chunks of data or groups of data on the medium. At the data link layer, those chunks are referred to as frames, and don't call them packets. Made that mistake in Tullis's class once. I called it packets, and he called me out, and I was kind of embarrassed. But data link pieces of data are called frames, and so let's talk specifically about Ethernet frames. So this is currently the most popular data link standard, mainly because Ethernet is everywhere. And a lot of like you notice Wi-Fi and Ethernet are kind of similar. Wi-Fi has some extra stuff, to deal with wireless stuff and all that. But if you notice, like this is a MAC address. The Wi-Fi kind of uses the same thing, but we're not here to talk about Wi-Fi, so let's throw that to the wayside. So each Ethernet device is assigned a 6-byte MAC address at manufacturer, and it's represented here as hexadecimal, like a colon-separated hexadecimal. And here the first 3 bytes is the OUI, or the organizationally unique identifier, words, which identifies the manufacturer of the device. And the second half of the MAC address is specific to the device, according to manufacturer. So this is supposed to be in theory so that all devices have a unique MAC address. And that should never change. It's usually burned in on the factory, or it's provided via software. But it's not impossible to change it, especially if it's like provided in the software. Like Android, many Android phones have it in the software. It is possible to change your MAC address to do some sketchy things. But yeah, it's just kind of interesting. Yeah, and the network interfaces. So whenever a network interface receives a frame, so whenever your Ethernet port receives a frame, it will check your device will check like the first 6 bytes of every frame to see, okay, does this equal my MAC address? And if it doesn't, then it just throws it to the wayside. Okay, that message isn't for me. But if it is either of these, so if it matches the interface MAC address, or the MAC address is a broadcast, or if it's multicast and you're in the multicast, which is something used on routers, we're not really going to talk about that much. But then it has to send the data up to the next layer, which we'll talk about in a little bit. But there's this problem at layer 2, more at layer 1, but whatever. But what happens when 2 devices transmit on the same medium at the same time? This is called a collision, which means data is lost. On Ethernet, you could detect a collision on the same link if you could detect a spike in voltage. Then both sides know, okay, there was a collision. Let's try that again. But essentially, we're not going to get too far deep into that. Essentially, what you need to know is a collision domain is a section of network where transmissions of 2 devices can collide, and which you can only transmit 1 device at a time, or also known as half duplex. And ideally, you want these collision domains to be as small as possible, because you don't want huge networks where everyone has to wait their turn to broadcast or send a message. And hubs, the problem with hubs, mainly because they're so dumb, they can't separate collision domains. So collisions often happen when there are hubs, which is why a lot of networks don't have hubs anymore. They replace that with switches. And only one device in a collision domain can transmit at a time. So, yeah. Solution, the switch, which is a layer 2, essentially a smarter version of a hub, which you can check all the layer 2 information. So it checks the destination and the source MAC address in the layer 2 frame. And then it maintains a switching table, which is essentially mappings of MAC addresses to each interface on the switch. And it says, okay, this device transmitted on this port. I'm going to keep track of that so that if I get a message for that device, I can only send that on that port and I don't have to send it out all the other interfaces. Which can make networking, speed up the speed of your networks because you're not transmitting as much on every link. And the only thing is, on a switch, broadcasts always transmit out all ports. So you got to keep that in mind. You want to, we'll talk about that in a little bit. But this does break up collision domains, which is good for you. Now we're going to talk about the internetwork layer, aka the internet layer, which facilitates communication between two networks, 2 or more networks, I should say. So we have all these layer 2 networks. What are we going to do to connect them? We got to have an additional layer on top that facilitates connecting, so we don't have every device on the same layer 2 network because of broadcast. If broadcast, every device has to stop and read a broadcast. So you have to reduce your network size so that doesn't happen every time for every device on the earth. The prevailing standard for IP or internet layer is IPv4 and IPv6. IPv4 is kind of something we're trying to kill off because we're already out of IPv4 addresses, but IPv6 is not catching on yet. Which IPv6 is about better in every way, but people are stubborn and we're still using IPv4 to this day. And every layer 3 or higher device has an IP address. So a hub would not have an IP address. Switches, if they're only in layer 2, there can be layer 3 switches, but we're not going to talk about that. Layer 2 switches do not have an IP address, but routers and computers and your phone, all those have MAC addresses. And data sent in chunks at this layer is called a packet. So this is where you get like all that packet loss stuff from the internet layer. So we're going to talk about IPv4. So in IPv4, every device gets an IP address, which is 4 bytes long, 000 to 255, 255, 255, 255. Which, fun fact, near those are actually valid IP addresses, but I digress. These can change. They can change as a device changes networks. So a device might change their IP address, but in theory, they shouldn't change their layer 2 MAC address. And this is assigned statically or via DHCP or some other configuration protocol, which basically is how a router or server on the network can tell each host, hey, use this IP address. And also, this is where our DNS servers are, or this is the default router, all that kind of stuff. That's all DHCP. Also, every IP address has 2 parts. There's the network part, which is the first part, of course, and then the host, which is the second part of the IP address. So, and that is that where that separation occurs might be different for every IP address. So we need what's called a subnet mask to define to each device, okay, this is where my network ID ends and this is where my host begins. And every network, IPv4 network, has two reserved IP addresses, which is the network ID, which has all the host bits set to all 0, and the broadcast, which is all the host bits set to all 1s. So the broadcast is used when you want to send a message to every device on the network, and if you do that, it tells layer 2 like, okay, I'm gonna go send this out to all Fs, the broadcast MAC address. So that's how that works. And now we have this thing called a subnet. What's a subnet? Well, a subnet is basically a subdivided network. So whenever, because IP addresses are so scarce, you need subnetting to kind of divide your networks into smaller portions that you can logically filter out throughout your domain or your network. So you can have one subnet that's like for your accounting, one subnet for your computer labs, one subnet for your VoIP phones, all that good stuff. So it's just a way to subdivide your networks into smaller networks. So what we need here, we kind of touched on it, but what we need is a subnet mask. So subnet mask is an IP address with all network bits set to 1 and host bits set to 0. And that's sent out via DHCP or statically configured so that each device knows, okay, what part of the IP address is network, what part is host. So for example, in this 192.168.132 with the net mask 255.255.255.0, the 192.168.1.0 part of that IP address is the network and 32 is the host. And then we also have CIDR, or classless interdomain routing notation, because the subnet address, yeah, it's useful, but it's really long. Like, I don't want to type out 255.255.255.0 every time I'm configuring a network interface if you're statically configuring things. So CIDR notation allows you to represent 255.255.255.0 as the number of bits that are set to on in your network ID. So for this, there would be 20, because this is 4 bytes long and 3 bytes are 255. The CIDR notation would be 3 times 8 for how many bits? That would be 24. So this would be /24. For this network down here, 10.0.0.1/8, 10 would be the first 8 bits, which is first byte. 10 would be our network ID, and 001 is the host for this IP address. And a little bit more explanation here. So we have this convoluted IP address right here, 192.168.35.160/25, just to show you that it doesn't have to stop at these dot boundaries. It used to have to do that when we had classful routing, but we're now we have what's called classless routing, which is what this thing is kind of derived from, the /25. But basically, the subnet mask is 255.255.255.128 in this instance, because this one is the 128 slot. So that is what it is here. So in order to figure out, so whenever a host gets an IP address and it needs to figure out, okay, what is my network ID and what address do I broadcast on? The host the net mask you see down here is all ones. Oops. It's all ones. And then the host part is all zeros as it's highlighted down there. And it's ANDed together by the end host. And so we have everything. It's essentially just copying everything up until we have all these zeros into the network ID. And then the broadcast is the same thing, but we take all of that and then we set everything to 1 in this host ID column, or in these host ID bits right here. So, and then you convert that back up to, well, the host wouldn't, because this is what it's actually reading. But for humans' sake, you could convert that back up to decimal, and you get 192.168.35.255 for this broadcast address, right? Although I think I made a mistake and I put the wrong bits here. This is actually 192.168.130.255. So, my bad. And also at the internet layer, we have these things called routers, very important. They connect 2 or more networks. You can kind of think about routers as they separate the 2 networks from each other. And they separate broadcast domains. So broadcasts travel through switches, but not through routers. So this is useful if you want to limit the amount of broadcast traffic on your network. You could subdivide it using a router, and you can keep it because lessen that traffic. But one thing to keep in mind is you kind of have to keep a balance, because a router is slower than a switch because it has to go up and read more information in the layer 3 packet, whereas a switch only reads up to the layer 2 frame. So there's more processing in a router. So generally they can be slower than a switch. So you kind of want to balance switches and routers. You wouldn't want to have every device connected to your router because it would be super slow. And routers have this thing called a routing table. Actually, every device has a thing called a routing table. And this is a mapping of what networks are available through which IP devices on your network. This lets a device figure out where they're going to send their packet so it can get to their destination, or it lets it figure out their next hop, which usually is a router if you're an end device. And it's populated. How this gets filled up is using, either you can enter in static routes, it's called, or you use a protocol, which I'm not really going to get into, but because it's only really with inter-router, this is all on a host. It just kind of figures it out. But anything that's not directly connected, any device that's not directly connected has to be configured with a route, either statically or dynamically, into this routing table. And usually that's handled by a router. And one route that you need to remember is 0000. Whoops, did that again. Which is the default route. And this is where you send traffic. Like, I don't know what network this is. I'm just going to give it to this person. He'll know what to do with it. And this is how the internet works. Like, you don't have Google's network in your routing table. You have 0000 because Google isn't your next hop. Your default router is your next hop. So 0000 is usually set to your default router. It might not, but it usually is. But how do we know the MAC address so we can tell layer 2 what device to send it to? Because remember, layer 2 only works in the MAC address world. Well, that's what this thing called an ARP table does. So this maps layer 2 MAC addresses to IP addresses. And this is populated using ARP, or it can be statically configured. But and ARP is kind of a bridge between layer 2 and layer 3. And it works by broadcasting out on the network, essentially, hey, who has this IP? Tell me at this MAC address. And then the host who has that IP address, if it exists, will reply, hey, I have that IP. My MAC address is this. And then that will go into this routing table. And so this allows layer 3 to tell layer 2, okay, so this is my next hop. Just send this data, shoot it at this MAC address. So that is how layer 2 and 3 can kind of talk together. Now we're getting into the transport layer, climbing up the stack. The transport layer handles getting data to the desired application. It is a 2-byte. It uses a 2-byte port number to identify each application. So HTTP usually uses port 80. HTTPS uses port 443. Those are essentially numbers that represent which application you're going to be sending your data to once it gets to the host. Also, there are 2 common protocols at the transport layer, which we'll talk about. TCP is reliable and handles sessions, which is also the next layer, which we'll talk about in a bit. And UDP, which is fast and doesn't protect data loss. And chunks of data at the transport layer are called segments. So first we had frames at layer 2. Layer 3 internet had packets, and now we're at layer 4 transport with segments. So TCP here, which stands for Transport Control Protocol, and it kind of has layer 5 as well, as I just explained. It has all sorts of fun control flags like SYN, SYNAC, ACK, FIN, reset, all those stuff. We're not going to get too far deep into what each of those means, but the ones you need to know are the ones used for the 3-way handshake, which is SYN. So whenever a device wants to open a TCP connection with another device or another application on another device, it sends a SYN segment, and the device will respond with a SYN-ACK segment, as demonstrated in this tweet. You know, hey girl, you a TCP packet because you looking like a snack. You know. Anyway, and then ACK is what the host responds with once it receives that SYN-ACK, and that finishes the 3-way handshake. And then every segment from then on has an ACK flag set, and if it doesn't have that set, then it gets rejected. And then when you're done, you use FIN-ACK to close. And also TCP uses sequence numbers, which it helps if the data arrives in out of order. It can put it back in order by using the sequence numbers. Like, okay, this is segment 6. I'm waiting for segment 4 and 5 to arrive here. Okay, there they are. And now I can reconstruct the data in that order, 4, 5, 6. So the application gets all the data in order it was sent. And now we're going to briefly gloss over UDP. Essentially, all it has is destination port, CRC, cyclic redundancy check, which basically just checks to make sure the port wasn't messed up during transmit or whatever. A lot of the lower layer protocols had something like this as well, but I kind of glossed over it. And then that's about it, you know. And this is good for when speed matters over reliable data transfer. like in DNS, which stands for Domain Naming Service. Excuse me, but Domain Name Service essentially maps. Well, we don't talk about it very much in this presentation, but it essentially maps internet addresses like google.com and whatever, dsu.edu, and it maps it to their respective IP addresses. So essentially what DNS does is every computer wants to find out what IP address is linked to a URL or a domain name. It could yell out to DNS and it'll be like, hey, where's google.com? Where's google.com? Where's google.com? Where's google.com? And it just keeps doing that until it gets a response. And it doesn't really care if it gets there all in one piece, as long as it gets its response eventually. It'll just keep sending eventually after a timeout for DNS until it gets an actual response. It's like, hey, Google doesn't exist, or hey, Google. Oh, my hey Google went off, but sorry about that. But hey, Google is at this address. So that's kind of a little overview of DNS, but that uses UDP, unless you're talking about DNS over HTTPS, which is a whole different monster. Uses TCP, whatever. We're not going to get into that. All right. Now, you look at me and like, what is this monster of a slide? Well, this is the session, presentation, and application layer slide. And this slide, I grouped this all together because mainly the TCP/IP model is kind of like OSI, except for the top is all of these layers are grouped into one layer called application, which people still call layer 7, because the TCP/IP model is technically what is used today over OSI, but people still refer to everything as OSI. So, because OSI was a little more specific. But essentially, the session is what keeps track of what connections are open between your clients. And this is partially handled by TCP, so this is why things kind of get iffy up here. But also, HTTP has session cookies, which kind of represent the session at an application layer. So, they give you a session cookie so you can keep track. Okay, this person had this cookie. That means they must be this person logged into this site. So that's the session layer. Presentation layer is pretty much all it is what format is the data in for the application to read. And this could be file formats like GIF, PNG, JFIF, whatever, JPEG, all them different file formats. And this also includes if the data is encrypted or if the data is encoded in any way. All of that would be technically presentation layer. And then we have the application final result, which is the actual end program receiving all the data. And this is like example, the browser and your web server, both application level things, as well as Minecraft would be an application example. So they're what's receiving all this data. And essentially they're the top of the building. They're all the execs, and every layer below this is just getting data to the right place so that the execs don't have to worry about what MAC address. So the Minecraft doesn't have to worry at all about any MAC address stuff. It just worries about, okay, I need to get, it has to know something about your IP, which sometimes it has you enter an IP address for like a Minecraft server, or not. You can enter an IP or a URL or a domain, and it can use DNS to resolve. Okay, that's this IP address, and that's about as deep as the application goes. All it cares is it sends an IP address to layer 4, which is kind of why TCP kind of skips over it. And then it sends the data that it wants to send to that, and it gives it to layer 4 or layer 5 actually. Or no, wait, layer 4, because that's transport. And it says which port is like, here, you take this, I want to send it to here, do it lickety split, or you're gonna be in a trash can, Anyway, so that's pretty much it. A little bit of a skip there on the top layers, but any questions you guys have about networking in general? Open for any questions. Stop the timer. It is 41 minutes and 40 seconds. Any questions? No? Gonna wait 10 seconds. I'm also looking in the computer club's chat. You want to send something in there? Nope. All right. Well, before we leave then today, that's all I had. Project Demo Day. We are looking for presenters, like I said in the beginning of the meeting. They'll be presenting November 9th, Computer Club meeting. Just copy down that link. I'll leave it up for you guys. Also, I'll send it in the Computer Club's chat. It is also in the Slack. I'm going to be putting on the website as well. But if you have a project or you're working on a project and you want to show it off to all your peers, go ahead, sign up at that link, and you can present November 9th, pending approval. Yeah, let me put this link in the Computer Club's Discord channel. XA7, so you guys can click on that. There it is. All right, and that's all I got for you today. So, thank you for coming, and I'll see you next time. Discord channel XA7, so you guys can click on that. There it is. All right, and that's all I got for you today. So, thank you for coming, and I'll see you next time.